Hello students, today I am going to make you understand about the assumptions related to limit state of collapse. It is based on IS 456-2000 which is Indian Standard Code. The assumptions we will use for the designing process of the flexural members like beams. In which we are going to study about the neutral axis, about the compressive strength of the concrete, about the tensile strength of the steel, about the stress strain diagram of the both of the material. So I will make you explain one by one each of the assumptions in details. So let's start. Now, as per the assumption in IS 456-2000, clause number 38.1, the first assumption says that plane section normal to the axis remain plane after bending. It means this in figure it's a given a beam. A geometry of the beam. The B says to width, the small d is effective depth up to the reinforcement, the capital D is the overall depth, and the E is the effective component. And in between this axis is known as neutral axis, NA. The assumption means that the strain is related to the height. As the height increases, the strain increases. Why I have shown in two parts? Because the beam is of concrete and steel both. So the neutral axis divides it in two portions. The upper portion is compression and the lower portion is the tension. So the strain from here to here it is compressive strain, and the strain from here to here it is tensile strain. Please see the figure very deeply that I have made the distance of the strain diagram up to the tensile reinforcement itself, because the tensile strain is due to the reinforcement, and above to the top because the concrete portion is up to the top. So here the values are shown. 0.002 is the maximum strain value. After that the strain become constant. It up to 0.0035. Which is maximum compressive strain. After that our our beam can be collapsed. As like that, the maximum strain of steel is 0.87 Fy by Es plus 0.002. Es is the modulus of elasticity, which is 2 into 10 raised to 5, and Fy is the characteristic strength of steel. So now in second assumption, it is mentioned that the maximum strain in concrete at the outermost compression fiber is taken as 0.0035. It means this is the strain diagram and the maximum strain is 0.0035. After that our structure get collapsed. So it is a limiting value that up to this much strain it is valid. After that it is not valid. And in third assumption, it is said that the relationship between the compressive stress distribution in concrete and the strain in concrete means if this is a neutral axis, then this portion will be compressive strain and this portion will be compressive stress, because this is strain diagram and this is stress diagram. So maybe assumed to be rectangle, trapezoid, parabola or any other shape. Means in this shape, in this stress diagram, up to the constant, up to the 0.002 value, the graph will be parabolic. But after that, the stress become constant and the strain will increase. So up to this value, it will be constant. So this portion will be rectangular, and this is the parabola. Or any other shape, which results in prediction of strength in substantial agreement. Means strain means what is the compressive strain, what is the compressive stress here. That we need to find. Here it is shown that the stress strain diagram of the concrete. So first we take the concrete compressive stress diagram. So up to 0.02 it is parabolic. After that it is constant. So this is the FCK value, means the characteristic strength of concrete, means the compressive strength of concrete, and it is as per given. But when we are using it at the field, the strength get reduced of a little bit. So we take it as a 0.67 FCK. It is a reduction factor 0.67. Okay. Now what is the design stress value of the compressive? So the design stress will be 0.446 FCK. From where we get that? So the design stress is get from this type. Means we have the factor of safety. Partial safety factor of concrete is 1.5. So design stress will be is equal to 0.67 FCK divided by gamma m is equal to 0.67 FCK divided by 1.5. So we will get the maximum compressive stress value 0.446 FCK. This is the maximum compressive stress value 0.446 FCK. Now from this assumption, the third number assumption, we will get the values of maximum compressive stress or maximum compressive force, or how we will decide that at this point, at which point the force will occur. That all I make you understand. So let's understand that. So as I said earlier in the assumption 3, that the shape of the stress diagram, either it will be rectangular, parabolic or trapezoidal. Here a beam figure is shown, okay, which is geometry. The strain diagram of the beam is given, and this is the stress diagram. Now it is noted from the top to the neutral axis. It is mentioned by XU, which is known as depth of neutral axis. XU is equal to depth of neutral axis. Now, as we study that from the center to 0.002, it is x2, and here it is x1. It means that up to this distance, the stress will be increased. After this distance, the stress will be constant. Okay, so the maximum compressive stress will occur at this point. Okay, so we need to find the distance from here to here. How much distance it is there? It is known as Z, or it is also known as lever arm. Okay, so how we will get this distance? Okay, this is effective depth D up to this, and this is x1. Okay, but it will depend on the diagram, on the shape of the diagram. So as we understand previously here, the maximum stress is 0.446 FCK. Okay, and the maximum tensile stress is 0.87 Fy. Okay, as the reduction factor is 0.446 FCK, like we find out like that, FCK, and then we add some reduction factor is equal to 0.5067 FCK, and then we divide by partial safety factor. So by dividing the partial safety factor, we get the value 0.446 FCK. Like that, in Fy also, there is no reduction factor because the steel is made in the laboratory. So the design stress will be dividing by partial safety factor, Fy divided by 1.15, the partial safety factor of steel, we will get 0.87 Fy design stress. So from that we get the value of this. Okay, now The maximum neutral axis depth of neutral axis is XU. So I can write that for 0.0035 the depth is XU. Okay. So and for 0.002 the depth is X2. For 0.0035 the depth is XU and for 0.002 it is X2. So what will be the value of XU? Yeah, X2. We need to find the value of X2. So X2 is equal to, I can say that 0.002 into XU divided by 0.0035. That we will get 0.57 XU. So the X1 distance is equal to XU minus 0.57 XU. So we will get 0.42 XU, which is the depth from here to here. This is 0.42 XU and this is 0.57 XU. Okay, now what is the maximum stress value, compressive stress value? So the total stress is depend. Total stress is equal to summation of area of both portion in the sense rectangle portion first one and second one is parabolic portion. So the summation of area is equal to area of rectangle portion plus area of parabolic portion. So area of rectangle portion is equal to 0.42 XU into 0.446 FCK. That we can write. Then plus second portion is area of parabolic. The area of parabolic is equal to 2 by 3 base into height. So 2 by 3 base is equal to 0.446 FCK. Base is equal to 0.446 FCK into height 0.57 FCK XU. So the answer we'll get is equal to 0.36 FCK XU, which is maxi total stress 0.36 FCK XU. Okay, I hope you understand that from the value 0.42 XU is come, 0.57 XU is come, and total stress of compressive stress is 0.36 FCK XU, which the third assumption statement was proving. Okay, so now moving in the further assumption. Fourth assumption says that the tensile strength of concrete is ignored. Obviously, it will be ignored because the concrete is weak in tension. That's why the value of tensile strength is ignored for the concrete. Okay. Fifth point says that the stress in the reinforcement are derived from representative stress strain curve for the type of steel used. But we are using the reinforcement, so the tensile stress will be occur due to the reinforcement used in that. So what will be the stress and strain value? It will depend on which type of the reinforcement we are using. So there are three types of reinforcement as I have mentioned you earlier. That first one is mild steel. Is equal to 250, whose characteristic strength is 250 Newton per mm square. Second one is HYSD bars, means high yield strain deformed bars, whose characteristic strength is equal to 415 Newton per mm square, or we can say that 500 also. Then third one is TMT bars, is 500 or 550 end or line end 550 Newton per mm square. So it will depend on the value of which type of steel we are using. So I will explain you by using the mild steel. Okay, here it is shown a stress strain diagram of tensile stress of reinforcement. So the stress is Fy, okay, maximum, but design stress is 0.87 Fy. That I have explained you earlier by which 0.87 Fy value comes. Okay, so we are going to find the stress strain value. So for Fy is equal to 250 Newton per mm square. So the maximum stress, design stress will be 0.87 Fy. So it will be what? 0.87 into 250. So we will get 217.5 Newton per mm square. Okay. So at that time, what will be the design strain? What will be the design strain? Generally, we know the equation that modulus of elasticity is equal to stress upon strain. So we can write that strain is equal to stress upon elasticity. Okay. So here 0.87 Fy divided by Es. This we can write. So the design strain will be 217.5 divided by 2 into 10 raised to 5, which is the elastic modulusity of steel. Okay, so we will get the value of 1.03 into 10 raised to minus 3, something like this value we will get. Okay, so this is the design strain value. Okay, now if you want to find maximum strain value, then the equation is 0.87 Fy by Es plus 0.002, which I have shown you in the strain diagram. Okay, so we need to add this portion and we will get the value 3.03 into 10 raised to minus 3. Okay, so this is the design stress, design strain, and this is the maximum strain value. So like this we can find the values of stress and strain for different types of steel. Okay, if you want to find the HYSD, then we need to write here 415. If you want to find the TMT bars, then we need to write it 550. Any type of steel besides of these three types, also we can find the design stress strain value and maximum like this way. This is the fifth assumption is explaining. Okay, so now moving to further assumption. The last assumption of limit state of collapse says that the maximum strain in tensile reinforcement in the section at failure shall not be less than 0.87 Fy by Es plus 0.002. That we have understood in previous assumption. But on the basis of this, we can decide the depth of the beam. We can decide the depth of the beam. So how it is possible? So here I have make one strain diagram of the beam. This is neutral axis. If we are on the limit state, okay, then we can say that XU is equal to XU max. This is a balanced position. Okay, the both will be equal. So I can say that this is a limiting value, means the maximum value. So for XU max, the maximum strain is 0.0035. So what is the maximum strain for D? It means XU max by D. So I can say that XU max is equal to 0.0035. For XU max, 0.0035. And for D, the whole will be considered. So whole means it will start from the 0.0035 plus 0.87 Fy upper Es plus 0.002. So I can write it like this: 0.0035 divided by 0.0055, the summation of these two, and 217.5 divided by 2 into 10 raised to 5. I am finding it for milestone. For milestone it is 217.5. After summing this or solving this, we will get the value 0.53. So xmax by t is equal to 0.53. It means that if we are using the mile steel, then the depth will be decided on the base of this. Like that we can find for the different steel also. It is as per IS 456 value, and the values of each steel is given in IS 456 page number 70, which is shown here. Okay, so I hope you all understand all the assumptions that I have explained you today. If not, then please comment me. Then I will make you more easier to explain. Okay, and we will meet in next lecture very soon. So up till that, be happy and be safe. Bye bye.